Our speaker today is Patrick Naylor from Princeton University, and he's going to tell us about doubling Glock twist. Thank you, Patrick.
Cool. Okay, we'll get started. First of all, thank you very much for the invitation to speak. I'm really excited to be here. Some of you may know that in the fall of 2019, I spent a term visiting Dave and people here. So what's that?
Oh, sorry, just checking that the volume is good.
Oh, okay, cool. Anyways, yeah, it was. I spent a term here in the fall of 2019, and I had a lot of fun. And it's cool to be back here giving a seminar talk. Obviously, circumstances are what they are, but still really cool to be here. And yeah, thanks to all of you for showing up and listening to me talk. Okay, so I want to talk to you today about a project that I'm kind of excited about. It has to do with doubles of Gluck twists. There's a little, I'll put a little asterisk, especially because I'm being recorded, which is this project is not written down yet. So, you know, take it with a little grain of salt, but I'm really excited about it. I think it's really cool. This is, of course, joint with Dave Gabai and Hannah Schwartz. Is there anything else that I want to say? Yeah, that's about it. I mean, so I think the talk is going to be kind of fairly light and breezy. I don't know what the weather is like there, but it's fairly nice here. So we'll talk about some Gluck twists, talk about some history and some stuff that we do know. I'll talk to you about what we did, which is sort of, I think, another look at maybe an old perspective, which is pretty cool. And then we'll call it a day. Okay. So let me start with an extremely impossible motivating question that I will not speculate on in this talk, but will serve to sort of motivate this. I'm sure everyone is familiar that the smooth four-dimensional point create conjecture asks the following question. It says, if you have a smooth four manifold that's homotopy equivalent to the four sphere, then it's diffeomorphic to the four sphere. Okay, so we know the answer to this question basically in every other dimension, every other choice of word here. So if it's, you know, if you replace that word with homeomorphic, the answer is true. Sort of true in small dimensions for classical reasons, dimension 3 by Perelman, dimension 4 by Friedman, and higher dimensions by Smell and some other people. It's false smoothly in other dimensions as stated. You know, in dimension 7, there are of course exotic 7 spheres, but it's wildly open in dimension 4. So this is sort of the theme of the talk, maybe. So for us today, everything is four-dimensional, orientable, unless I say otherwise, and smooth. Okay. So, you know, if you're going to tackle something like this, what do? You try to construct sort of interesting examples. And so there's this sort of common theme that happens in four-manifold topology in which people construct potentially interesting examples of homotopy four spheres and say, okay, what about this? This doesn't look like it's obviously S4. What can you say? And then other groups of people go on and show that, oh, in fact, those things are standard. In other words, they are diffeomorphic to S4. And then people go back and they construct sort of ever more elaborate, you know, homotopy spheres, and people show their standard. And that's sort of, you know, what's happened for the past while. Lots of interesting examples, basically alternating between interesting constructions and interesting standardizations. Okay, so there are lots of interesting constructions, but there's one construction I think has sort of stood the test of time, and that's this Gluck construction. So I'll tell you or remind you what that is in case you've never seen that before. Okay, so it's a construction. It's a very, very general construction that will start with an embedding of a two sphere and a four sphere, and it will spit out some sort of four-dimensional homotopy sphere, which everywhere and from here on and forevermore, I'm going to denote sigma sub s. So it starts with a two sphere, some smoothly embedded two sphere, and spits out a homotopy sphere. So I'll tell you how this works. So in 1961, 62, Hermann Gluck was studying, for related reasons, the mapping class group of the 3 manifold S2 cross S1. Okay, so this is diffeomorphisms of S2 cross S1 up to, say, isotopy, allowed to move points in the image around. And so he studied this group and found that it's not only is it finite, it's 3 copies of Z mod 2. Okay, and some of them are not super interesting. 2 of them are generated by reflections. 2 of the copies, that is. What can I do? I can reflect across, let's say, this sphere, or I could reflect across this sphere. Not super interesting, but there's one other element in this mapping class group that is kind of neat. And I'll again, sort of from here on and forevermore denote this by tau. And you can write this in coordinates. Let's say if a point on the 2 sphere is x and a point on the circle is theta, then in coordinates, this looks something like this. So what do? As I go around the circle, I leave the circle factor alone. But depending on where I am on that circle, I rotate the 2 sphere by, let's say, theta amount. Okay. So I'll draw like a schematic to make sure everybody's on the same page about what this map is doing. So here's on the top here, this is like an interval's worth of 2 spheres I've drawn schematically. Really, I want to think of it as a circle's worth of 2 spheres if I glue the ends together. And here's maybe some like reference arcs I'll just draw, just so you get a sense of where everything is going. And under this map, what do I do? Well, as I walk through the circle direction, I rotate these 2 spheres, by a certain amount till I get back to where I started. So maybe the first one gets left alone. The second one rotates a little bit. This next one rotates a little bit more until I'm back to sort of where I started. Okay. It's a smooth diffeomorphism of S2 cross S1. And usually we always call this this is like the twist map. Before I go on and sort of jump into the deep end, are there any questions about what that map is, what it's doing? Is that sort of everybody okay with that? Okay. Okay. Why is that interesting? Well, here's what you can do. So if you have a 2 sphere smoothly embedded in the 4 sphere, well, then everything is null homologous. So a regular neighborhood of that sphere is trivial, looks like S2 cross D2. And so the boundary is S2 cross S1. Okay, so you can, if you want, you could take that embedded 2 sphere in the 4 sphere, look at a regular neighborhood, cut it out, and reglue it by basically any automorphism of its boundary. And what this theorem of Gluck tells you is that there are basically only maybe 8 choices at most, right? If I take it out and put it back in by the identity map, then I haven't done anything at all, and I've just rebuilt S4. But what I could do is I could take it out and reglue it with this twist. And that's the sphere that, or the manifold that we'll call the Gluck twist on S. So I remove a neighborhood and I reglue it with this twist map. Okay. And it's a very reasonable question to ask, is this S4? Because it sort of looks like S4. As sort of an aside, I only sort of realized this a month ago, so I want to like share this with you. This tells you that 2 spheres, embedding 2 spheres in the 4 sphere might not be determined by their complement. This is true for knots. Knots are determined by their complement, but 2 spheres in general sort of might not be, because you could remove a 2 sphere and reglue it in, and if the result of that construction gives you back S4, and the 2 knots you consider are not equivalent in some sense, then they have the same exterior. So there are examples of Gordon where this actually does happen, which I thought was kind of interesting. Anyways, this is the Glock construction. So some things that a person should check. This really is a homotopy 4 sphere. How do you sort of vaguely at a high level see that? Well, this map, I mean, it is the identity on pi1 because I literally fix a generator for pi1. And so you do a Van Kampen sort of thing and you can check that it's actually simply connected. So that's a good start. If you write down some exact sequences, you can check that H2 of this manifold is actually 0. And then because it's a 4 manifold, actually all of the homology vanishes. And so now you've got a homology sphere that's simply connected. And so there's a theorem of Whitehead that tells you that such things are homotopy equivalent to spheres. And even further by Friedman's theorem, or in other words, the Poincare conjecture topologically in dimension 4, this thing is homeomorphic to the 4th sphere. So it's like very close, looks very much like the 4-dimensional sphere. But it's a very good question. Are these Gluck twists diffeomorphic to S4? And this has been essentially open since the 60s, which I think is very interesting because it's a really explicit construction, but somehow it's, it's tricky. There are a lot of embeddings of 2 spheres. I have a little note that says non-orientable examples. There are examples where doing this operation can change the smooth structure. So far as I know, there are no simply connected or orientable examples. Oclu, I think, has a Gluck twist on this manifold. The twisted 3-sphere bundle over S1 connected some with 2 copies of S2 cross S2. There's a Gluck twist on that can change the smooth structure. But in the orientable case, and certainly S4, we have no idea. Okay, so that's sort of that's the question that I want to study for this talk. Before I go on, is there any questions about that? Yeah.
Question. Are you saying that in no matter what form manifold you do it in, it doesn't change the homotopy type?
I'm not making that claim here. I think that might be true, but I'm not sure.
When you say it changes the spin structure, it's not saying it changes the manifold, though.
Smooth structure.
Smooth structure. Yeah, it's Okbulu's example. I mean, I haven't read this paper all that carefully, but my understanding was that there's a Gluck twist on that manifold that changes the smooth structure. So you do a Gluck twist and you get something homeomorphic, but not diffeomorphic to that. But that's all I'm claiming. So I think that if your sphere that you start with is null homologous, I think that you don't change the homotopy type.
Right. I was trying to make Gluck somehow originally proved that this diffeomorphism does not extend across S2 cross E2, and I thought maybe he proved that by just showing some particular form manifold in which it actually changes the homeomorphism.
Oh, that's it. No, I don't. I think he might do it directly somehow. Like I think he. I don't remember exactly how, but I think he somehow shows that the like something will extend if and only if it's like in this subgroup of reflections. But I don't actually remember the like details of that.
Thanks.
Cool. Great. Okay. Any other questions? Okay. So right. Is the Gluck twist ever diffeomorphic S4? So the answer is yes, sometimes. And so here are some examples where we do know this is the case. There are a bunch of them. So the first, so maybe if you've never thought about embeddings of 2 spheres and 4 spheres before, this might be like a good time to think about some. So here's the easy thing you can do. It's called a spinning construction. Start with your favorite knot in S3. My favorite knot in this picture is the trefoil. Puncture it so that you get a tangle in the 3 ball. And then you can do what's called spinning. You can spin this tangle. And so you imagine S4 or R4 built as like a fibration of B3s or half open R3s around some sort of axis. And you spin that knotted tangle around sort of through 360 degrees, and you get an embedding of a 2 sphere in 4 space. This is like not super, not really unrelated to the knot that you start with. It has the same fundamental group. The complement has the same fundamental group, but it's an interesting, interesting looking embedding of a 2-sphere. It's knotted non-trivially. And Gluck originally showed that actually, okay, Gluck twists on these spheres give you back S4, always. Very good, okay. So there's something else that we can do. I'll sort of make a little, it's like a trivial looking observation, but you'll see why in a second. So one way to think of these spheres is you can imagine if I cut that sphere down the middle along a cross section, like the one that I sort of drew here, what do I see? Well, I've decomposed the 2-sphere into 2 disks. They're both the same disk, and on the boundary, I see the knot K connects on with minus K, right? Sort of like I've drawn here. And it's minus K because when you come back, you get the opposite orientation on the knot, basically, or the mirror of the knot. And so that's, that's sort of, it's maybe a silly observation, but you can write S4 as the union of these 2 4 balls together with this sort of disk on the inside. And that's a particularly nice slice disk for K connects on minus K. It's nice, obviously ribbon. Okay, that's fabulous. What's the point? The point is you can always make that construction look worse if you really want. So for example, you can insert your favorite concordance in the middle. So in other words, if I have a concordance from, let's say, K connects on minus K back to itself. So in other words, an embedded annulus bounding K connects on minus K on both sides inside of S3 cross I, right? Then I could glue that in. And so, I'll glue B4, a copy of S3 cross I, and then another B4, I'll get the 4-sphere back. And I'll have this disk for K connects on minus K, an annulus connecting them, and then the same disk again. And so I'll get some, new, maybe more interesting embedding of a 2-sphere and a 4-sphere. And so that's, that's something we can do. We can invent lots of concordances like this. Here's one in particular. I'll call it like the twist concordance. Here's K connects on minus K. Here's something you can do. Imagine rotating this summand through 360 degrees. You take that summand and you just rotate it through. And you can build a concordance just by looking at the trace of that isotopy, right? So I can put that in. Maybe I'll call that concordance C sub T, and I'll call the resulting 2 knot that I get, I don't know, T sub n of K. Because I could do this, I could do this as many times as I want. Maybe I want to do it n times. And yep.
Sorry, maybe you said this already, but what is the trace of an isotopy?
The trace of an isotopy. So I just want to imagine. So I'll imagine. Right. Okay. So there's an isotopy of K connects on minus K, which is a smooth motion. In this case, from that knot back to itself. What I'll do is I can construct an embedding of, let's say, S1 cross I inside of the ambient space S3 cross I, where at every time, what is the annulus? What does the slice of the annulus look like? It's just that time in the isotopy. So I like. Does that make sense? Should I try draw a picture?
Picture would be nice. Thank you.
Cool. Yeah. Okay. Okay. So here's, so okay, you have maybe here's S3 cross I. That isotopy is like is something that depends on T. And it, at each time T, there's some image of that knot. And what I'll do is I'll just put, at each time T, I'll just put the image in as a slice. And that constructs like an annulus as I built. It's like I could write all of this out as sort of like coordinates, but yeah, that will build for you an annulus embedded in S3 cross
Is it
by
supposed
looking at each slice.
Is it supposed to be S1?
Or sorry, S1 cross I embedded in S3 cross I.
Right.
You wrote S2 cross I in the top left.
Oh, did I? Oh, sorry.
Next to your name.
That makes more sense. Great. Okay, good. Does that make sense?
Yeah, thank you.
Cool. Okay. Yeah, so that's a, you know, potentially maybe more interesting class of embeddings of two spheres. They're called twist spun knots. So theorems of Gordon in 1976 and Pao separately in 78 tell you that the Gluck twists on those things are S4. And these are like a little bit more interesting two spheres. For instance, the knot complement sometimes can have torsion. So they're not, the complement of these things sort of does not look like a one-dimensional knot group. Okay, so that's all fine and dandy. You can make this worse if you want. You can do something called a roll spun knot. So again, we're going to do the exact same construction. I'll think of S4 as being built from B4, another B4 with these same disks in them for K connects and minus K, and I'll insert a concordance of some new kind inside of S3 cross I. And the concordance again will be the trace of some isotopy. What should I do? Okay, here's another copy of my knot, K connects and minus K. The isotopy that I'll do that takes it, you know, back to itself. I'll imagine one sum end as being very, very small, and I'll drag it through the other sum end. So it comes along, comes down this strand, comes through, comes back around, and it comes, gets spit out and winds up back where it started. So that's, we'll call that like the roll concordance, maybe like C sub R, and then maybe the resulting two sphere I'll call Rn of K. Okay, and again, because I could do this as many times as I want. Okay, so somehow that's like a little bit more interesting two sphere, even more interesting than twist spun knots. That concordance or that isotopy really sort of messes things up. The other examples come with like a really nice, they come with like a really nice circle action. Like they look sort of like a, you can really see a circle's worth of something happening. Here, this concordance really sort of destroys a lot of that. And so surprisingly enough, it's an open question whether Gluck twists of roll spun knots are standard. We don't know the answer to that question as far as I know. There are some things that are known. If you have a torus knot, for instance, then we do actually know the answer to this question. But these are interesting knots. I mean, they're always non-trivially knotted, basically. If the knot you start with is fibered, it's not even ribbon. If you're familiar with this, the fundamental group of the complement is never a one knot group. They're quite interesting. So there are some things you can say. So Hannah and I thought about this 2 years ago. And we came up with the following. So we said if the unknotting number of the knot that you start with is 1, then the Gluck twist on that roll spin is S4. But that's all we were able to say. The proof really needed this fact about unknotting numbers. It was not sort of obvious to us how to extend it to a higher unknotting number. This is it's like a complexity assumption. And so it's going to be a theme you'll see sort of at the conclusion of the talk is that if you impose kind of a complexity assumption like this, you can say something in general, maybe not. Okay. Any questions about these sort of constructions maybe before I go on? Cool. Some other things, we do know other cases. Those are all like a very specific sort of brand of construction where you use these nice looking discs. There are other things, ribbon knots, if you're familiar with these, particularly nice immersion. More generally, there's a notion of, it's called zero concordance in Paul Melvin's thesis that relates embeddings of two spheres in the four sphere. In fact, until quite recently, that this relation that I won't really tell you much about was sort of speculated that maybe all two spheres are related by this zero concordance thing. And actually, so UGA's own Jason Joseph along with a few other people. So Irving Dye, Maggie Miller, and then I think also Nathan Sanukian, all sort of gave independent proofs that no, the zero concordance thing is not enough to relate all of the two spheres. There are facts that we know about satellite constructions for two spheres. So Mark Hughes, someone Kim Maggie Miller have a paper where they say something about satellites of Gluck twists. Someone also has a paper on this. And then there are also some sporadic examples. Nash and Stipschitz have an example of where they show that a certain family of Gluck twists are standard, but it's really specific curve calculus, really specific to that set of examples. And then Gompf also has a really amazing paper where he shows that a certain homotopy sphere is standard. And it as it turns out, is a Gluck twist. But that's about it. Those are essentially all of the major families in which we know something about a Gluck twist, which is surprisingly small. I mean, I was able to tell you about it in 20 minutes, which I think is sort of, I don't know, I think that maybe highlights the fact that this is tricky, especially the roll spun case, because it's such a specific construction. I can tell you how to build it, I can tell you how to do a Gluck twist, and somehow it's hard to get a handle on it. So for the remainder of the talk, I want to tackle the following related, maybe easier, maybe equally hard question. So the question that I have is, when is it that the punctured Gluck twist crossed with the interval diffeomorphic to the 5-ball? So why is this a reasonable question to ask? So if the Gluck twist on a sphere S really were S4, well, then I could puncture it, or in other words, remove an open ball, and I would get B4. So for punctures, I'm just going to put a little circle above. I would get B4, and that tells me that when I cross with the interval, well, then I definitely get B5. Okay. But of course, it's like, entirely possible that maybe this is true, but the Gluck twist itself is not B4. So why is this maybe why would a person hope to ask this question instead of the original one? The theme is sort of that going up a dimension like this, or stabilization, or something along these lines, makes your life a little easier. So maybe handles cancel in a 5-dimensional setting that didn't in a 4-dimensional setting. Okay, so as sort of like proof of concept, or like a way to motivate, make you believe me, maybe, I don't know, you've never seen this before. Here's an example of exactly that happening. So here's a picture of a 4 manifold. If you're familiar with curve calculus, you'll recognize this as the Maser manifold. So amazing manifold, lots of properties. How do you build it? Well, you start with a 0 handle, you attach a 1 handle, this dotted circle here, and you attach a 2 handle along this sort of curve that seems to wind around a few times. Okay, and that's it. So it's not a closed manifold. Why is this interesting? Well, it looks like it might almost be the 4-ball, because this curve, this 2-handle curve, well, if you sort of keep track of it, it goes around once, comes back around through, and then it goes back down. So algebraically, the 1 handle and the 2 handle, they intersect in 1 point. And so, if you want to cancel handles, you need them to geometrically intersect at 1 point. Algebraically, it looks like things are okay. The manifold's even simply connected, because, I mean, the attaching curve for that 2 handle is homotopic to just like a little meridian around the 1 handle. That generates the fundamental group, so that that kills all of your fundamental group. So it looks like it might very well be the 4-ball, but of course it's not. This isn't the 4-ball because in particular it has the wrong boundary. So But what happens when I take this picture and I cross it with the interval? Well, I get the same kind of handle structure. So I get the resulting manifold is built with a 0 handle, a 1 handle, and a 2 handle. But what happens now? Well, the 2 handle is attached in the boundary of the 1 handle. It's attached in something 4-dimensional. And because this was homotopic to the little sort of S1 cross point here, well, the 5-dimensional 2 handle is homotopic to an S1 cross point in the new 5-dimensional 1 handle. But now you have curves in a 4 manifold, and homotopy implies isotopy for curves in 4 manifolds. So really, this is isotopic to S1 cross point, which means that that attaching curve hits this 1 handle exactly 1 time and geometrically cancels it. So when you cancel them, you're left with just B5. And so even though this is not the 4-ball, when you take the product with the interval, you get the 5-ball. And you sort of somehow crossing with the interval makes your life a little easier. What else did I want to say about this? No, that's about it. So hopefully that has convinced you. If you know this example already, then great. Something else that you sort of see from this picture is that the double of M, you glue M to itself along the boundary. That's the same as the boundary of M cross I, and so the double is S4. So if you heard the statement that the double of the Maser manifold is S4, this is sort of how you would go about proving that. And that's how that connects to the title of the talk. Okay, so unfortunately, if you start with a manifold that looks like this, and by looks like this, I mean is built with 0 and 1 handles, maybe it's simply connected, and it even looks like the handles cancel algebraically. It's not exactly obvious that when you take the product with the interval like this, that you get B5. There's a technical group theory condition that you need to impose to actually make that conclusion. This is sort of related to the Andrews-Curtis conjecture. So I won't say an awful lot about this. I sort of want to sweep this under the rug. In general, to make a conclusion like this, you need to know that the presentation that this 2-handle body structure induces on pi1, which you hope is the trivial group, it needs to be Andrews-Curtis. Andrews-Curtis trivial, in the sense that there are moves on the presentation corresponding to 1 and 2 handle slides 5-dimensionally that will let you sort of trivialize everything completely. So this conjecture, I think, is probably widely believed to be false, but there are no counterexamples per se. So this is sort of like this is a technical problem. I'm going to start taking products with intervals in a minute. And if at all possible, I want to avoid this problem. So this is sort of a dangerous thing. This is a dangerous thing to bump up against, because not only is it possible that you have a 2-handle body whose Andrews-Curtis presentation is not trivial, but we don't even have the technology to decide. This is like a really, really hard group theory problem that we want to just avoid. So okay, anyways, what else do I want to say? Something, if you look at products of puncture Gluck twists crossed with I, those manifolds are the 5-ball if and only if the double is actually S4. So of course, one direction sort of is clear, sort of the same observation I made before. If you have a Gluck twist, puncture it cross with I, and you get the 5-ball, well then, on one hand, S4 is the boundary of that 5-ball, but that's also apparently the boundary of this manifold. And again, that is the double of Gluck twist. So one direction is definitely true, and to go the other way, sort of, you've basically, if the double of the Gluck twist is S4, then in a sense you've constructed a homotopy 5-ball with boundary S4, and there aren't any of those because we know the smooth 5-dimensional Poincare conjecture. So fun fact. Okay. So great. So what do I want to do? I want to think about taking a Gluck twist, puncturing it, crossing it with the interval, and trying to find out when do I get the 5 ball. So that's what I'll talk about for the remaining time. How, like, what do you need to do? Well, you have to do a few things. So first of all, you need you start with a sphere. You need a handle decomposition, or at least some sort of presentation for that sphere. Starting from that, you need to be able to draw a handle decomposition, or like a Kirby picture for the Gluck twist. And then you also need to be able to look at, okay, what happens when I cross with I? And you're going to see what happens. So this is mostly, worked out and fairly reasonable. If you start with an embedding of a 2-sphere, you can draw it pictorially in a picture that looks like this, usually called banded unlinked diagrams. What is this a picture of? Well, it's a picture of the surface in Morse position, basically. Generically, if you put a surface in Morse position and you sort of walked upwards, what would you see? Well, you would see maybe some minima showing up. They grow to be sort of disks or circles, rather. Maybe you would see some index 1 critical points. So for a brief instant, you would see like a band, and then maybe some circles would emerge. And then you would, at some point, presumably, you might see some maxima. So you'll see circles becoming smaller and smaller and sort of disappearing into nothingness. And so you can draw these just exactly as this. So you would draw little circles like this for minima, where they sort of, time epsilon after they appear. Bands you would draw as literal bands in a diagram. And then if this, has been drawn correctly, the point is that after resolving all of these bands, I'm supposed to get an unlink, and that unlink eventually disappears into nothingness. So fun fact, the union of these, the resolution of these circles along these bands on the left actually does give you a 2-component unlink. So like in Morse position, maybe your sphere looks something like this. So 2 maxima and 2 minima. Okay, well, that's great. Point is, there's a standard recipe to take a picture like this and spit out a Kirby diagram like the one on the right. Okay, so I won't say a whole lot about this, because I think if you're familiar with Kirby calculus, you'll recognize this instantly. And if you are not familiar with Kirby calculus, this will sort of be meaningless. The point is, to each minima, you associate a 1 handle. So each minima, I get a dotted circle. It's basically a definition of a dotted circle. Each band gives me a 2 handle that looks pretty well the same as the original one, sort of links each of the minima. And then 3 handles, all 3 handles correspond to actually the maxima in this picture, which are the really confusing looking disks bounded by this unlink. Thankfully, we don't usually draw 3 handles, so I don't have to put it in this picture. Now, when I want to do the Gluck twist, it turns out all I need to do is attach a 1-framed 2 handle to one of the 1 handles. And it's actually, I won't say this, maybe think about it if you're not sure why. You actually can get away with 1 fewer 3 handle than you would otherwise need. So I'm happy to explain why later, but if you have M maxima, your handle decomposition, you actually only need M minus 1 3 handles. Okay, so to summarize this nice happy chart, if you have N minima, B bands, and M maxima, the punctured Gluck twist has a handle decomposition with N1 handles, B2 handles, plus this extra one, and then M minus 1 3 handles. And so when you take the product with I, you get the same number of each handles that you had for the Gluck twist. Okay, great. Any questions about that briefly? The recipe sort of makes sense. Cool. Okay, so if you accept that recipe, here's something you can think about. Suzuki spheres. So these are spheres, embeddings of two spheres that have only one maxima. So maybe they look something like this. So if you follow the recipe, well, there's only one maxima, right? And so that means that this 5 manifold, when I take the Gluck twist and I cross with I, can be built with no 3 handles. So there's only 1s and 2s. And actually, it turns out that it's a general fact. You have a nice presentation like this, the whole Andrews-Curtis problem sort of just goes away. So actually, this presentation that gets induced is Andrews-Curtis trivial. And so when you take the product with the interval, you really do get B5, which is kind of nice. Okay, so that's fabulous. What about more maxima? So if I go back to the example that I sort of drew earlier, that maybe looks like this: 2 maxima, 2 minima. Well, now what happens? So when I draw this handle decomposition, it will look something like this. I'll have like some 1s and 2s, and then now I actually really do have some 3s. And the hope is that maybe I can look at this handle decomposition. If I'm very careful, the 1s and 2s will give me B5, as long as I sweep all of the Andrews-Curtis stuff under the rug. And the 2s and 3s, I hope, will cancel. That's sort of like the basic idea here. And I'll be left with B5, which is what I want. What happens if there are more maxima? Well, okay, so Paul Melvin in his thesis has actually a really interesting recipe. So he tells you, he starts with a slightly different presentation than the one that I told you how to get, but very similar. And he tells you, okay, there's a relatively standard way with this only 2 minima to actually cancel those 1 handles. And then you could turn it upside down, turn that whole handle decomposition upside down, and you'll be left with, well, before you had 2s and 3s, now you're left with just 1s and 2s. And you see, okay, well, can I take that and cross it with I and get the 5 ball if there's no Andrews-Curtis problems? And unfortunately, that doesn't work, which is sort of sad. So Akblu and Kirby, in a series of papers looking at a different homotopy for a sphere related to the Kaplan-Shanison construction, do a lot of really hard Kirby calculus, and they show that, okay, this homotopy sphere they were interested in is a Gluck twist on some sphere. It's actually the union of 2 ribbon disks for the 8-9 knot, whatever, it doesn't matter. They go ahead, they run through Melvin's sort of idea of turning things upside down. They compute the presentation for the fundamental group, and they get something that is sort of widely not known to be Andrews-Curtis. In fact, it sort of appears in like standard potential counterexamples when you look up this conjecture. And if actually, so the presentation that they extract is even worse than this one. They extract your presentation, do a little manipulation, and get this one, and I'm not sure if this one's Andrews-Curtis. So that whole sort of philosophy just fails. You get stuck. Nonetheless, that Gluck twist is actually S4 by this sort of amazing theorem of Gabai. Anyway, the problem is you get stuck. Unless you're careful about all of these Andrews-Curtis things, you can't just freely mess with handle decompositions like this. So the idea that we had was, okay, maybe don't avoid them. Maybe don't, in all of these Kirby diagrams, we always avoid drawing the 3 handles because we don't want to think about them. They're hard to draw. This strategy of Melvin is to get rid of the 3 handles by canceling things and turning everything upside down. Maybe just don't do that yet. Instead, maybe you can get away with just studying them carefully. Okay, so I'll give you a theorem, and then I'll talk very briefly about the proof, and then I'll play some applications, and then I think we'll be done. Okay, so theorem. Suppose you have a 2-sphere, written as the union of 2 ribbon disks. Let's say D1 and D2. And suppose that this band pass number of one of the disks is 1. So you should interpret that as like a complexity assumption. One of the disks is simple enough. Then this conclusion follows. In other words, when you take the Gluck twist, puncture it, cross with I, you get B5. So in particular, the double of this Gluck twist is possible. So you'll notice there's no assumption on the second disk, right? This just says if one of the disks is simple enough, then this conclusion follows. And I think, you know, initially that really weirded me out. I thought that's really strange, but actually it's not all that strange because we made the exact same conclusion for these spheres. Because like somehow there's only one max. This is somehow like a union of two, you know, disks. Somehow the fact that this sphere is, or that disk is simple enough allows you to make this conclusion. The same thing is happening here. Okay, so what's this bandpass number? Very briefly, it's a number you can associate to a ribbon disk. What do? I'm allowed to take a band passing through a minima, or a band. I can just pass a band through a minima. And that's sort of weird. It's not well defined on two spheres, because in particular I changed the boundary of the disk. But I just look at how many times do I need to do that to get to like this extremely standard looking picture of a ribbon disk for the unknown. So if that number is 1, then we can make our conclusion. Okay, very, very briefly, ideas of the proof. The main idea is to use a slightly different handle decomposition for the Gluck twist, the one on the left. So if you're unfamiliar with Kirby calculus, this will look exactly the same. If you are familiar with Kirby calculus, so all that's happened here is that I changed which unlink I wanted to think of as the minima. So before I used these circles as the minima, and the really complicated unlink that I can't see very well was the corresponding to the 3 handles. The handle decomposition you probably should use is actually the other one. Make the really complicated looking unlink the minima, and make the 3 handles correspond to these really nice looking circles. Otherwise, the handle decomposition sort of goes the same way. Why would you do that? Well, it lets you draw, in some sense, it lets you draw the 3 handles. The 3 handles are sort of spheres in a 4-manifold corresponding to those circles. And although they're messy, you can actually draw them. You sort of take a sphere around one of these disks, inflate it a little bit, and then it's basically that sphere, except it maybe needs to go along these ribbons and get tubed over some 2 handles. That's kind of messy, but you can actually draw it. And then run through the same sort of argument. The 1s and 2s, if you leave them alone enough, will cancel, and the 2s and 3s, because you drew them so nicely, will actually cancel. That's sort of the idea of the proof. So really quickly, maybe some applications, and then we'll call it a day. This business of bandpass number being 1 applies to a lot of small disks. So for instance, here's a ribbon disk. It has bandpass number 1 because I can take this band, if I pass it through the minima, the whole thing comes undone. And it looks just like a really nice disk for the unknown. And again, there's no restriction on the other disk. So if I take, for example, any other ribbon disk with this knot as boundary, I glue them together, then if I think about the Gluck twist on that sphere, this conclusion about taking the product with the interval and getting V5 will follow. Which I think is really cool. It does imply that the unknotting number of the middle level section that you look at has to be 2. So that it's obviously not going to apply to all disks, but it definitely applies to a lot. For instance, it applies to the 8-9 knot. Those ribbon disks that I drew coming from this Blue Kirby example, you can draw, a little bit nicer pictures and convince yourself that those disks have bandpass number 1. It also applies to lots of other disks. Kawauchi has this excellent book on knotted surfaces in force space. And at the end, he has all of these ribbon discs for all of the ribbon knots of less than 11 crossings or something. And you can go through and just check, like, a lot of these satisfy this condition, which is, sort of interesting. And again, you could take any of these discs, glue anything you want to it, conclusion will follow. So I think that's kind of interesting. We have not really thought about, so at the beginning I talked about these spinning constructions and these slice discs for k connects and minus k. We have not thought super carefully about which discs of that kind satisfy this bandpass condition. I think some of them probably will. In general, maybe not. They seem to have a lot of bands, but yeah, that in itself would be interesting, because then you could say something about, for instance, some roll spins. But anyways, yeah, I think it's sort of a interesting phenomenon, if nothing else. But I think I'll stop there. Thanks for listening.
Thank you, Patrick. Any questions?
Well, does it help you at all trying to, knowing that thing cross I is standard, do you get any insight into trying to actually standardize the Gluck twist, or no?
Yes, we hadn't thought about that. I would hope, like, maybe, but I'm not actually sure how to do it. Like, I'm not sure what you would do. Because for example, like, it's just quite possible that it isn't. That does happen even for other manifolds. Yeah, I'm not actually sure, but it's a good question. One thing you can say, taking the Gluck twist is additive. So the Gluck twist on the double of S, or so the double of the Gluck twist of S, is sort of, well, is that really right? Oh yeah, okay. I guess this is really the same as the Gluck twist on S connects and minus S. So you are making a statement about Gluck twisted spheres of that kind. But I think that's about all I can really coherently say.
So go for it, Gordon.
Can you scroll back to that picture where you were like trading handles?
This one here?
Mm-hmm. Can you say a little bit about what you were doing here?
On this one here, you mean?
Mm-hmm.
Yeah, so all you want to do, so instead of using the sort of normal recipe, like this rising water recipe where you handles of the surface give you handles of the complement, just basically invert the picture of the sphere so that what you previously thought of as maxima for the sphere, so the sort of really confusing looking disk on the top, think of those as the minima and these as the maxima instead. So there's that corresponds to sort of changing every band to like a dual band in a sense, and then basically just apply the same recipe. And when you do that, you'll get this picture. So in particular, like these one handles, although they look absolutely horrible, they are actually unlinked. Because you started, the banded unlinked diagram had the property that when you took these circles, resolve the bands, you did get an unlink. So these really are unlinked one handles. And I'm pretty sure that if you just do that isotopy, that will take these really nice looking two handles to the two handles you used to see.
So, and what's the orange picture here?
Yeah, so the orange picture, so okay, so there's a related standard recipe for what, in this picture, what do the three handles look like? They basically look like inflated copies of this disk in some way. Maybe you can't really pass it through any of this, but maybe you tube it off to one of these two handles where you really can do that. But Okay, so what do you really do? Well, you take this picture, right? So this consists of, you know, 1s, 2s, and 3s. You cross with the interval, and you get a 5 manifold built from, say, 1, 2s. I'm going to separate out this special 2 handle. Well, no, maybe I won't. I'll just go to this. So I get 1s, 2s, and 3s. And what I'll do is I'll look at the 4 manifold that's living right here. So this is my 5 manifold. Look at this 4 manifold that lives here. So right between the 2s and 3s. And what is that 4 manifold? Well, it's the boundary of this 2 handle body, right? So really, this is actually the double. Maybe I don't know what else to call it. G. It's the double of the 2 handle body of G.
Okay.
So you look at that 4 manifold. So in that 4 manifold, what do you see? You see ascending spheres from these 2 handles, and you see, actually maybe I'll put that in green. You see ascending spheres for those 2 handles, and you see descending spheres for these 3 handles, living inside of that 4 manifold X. This is actually that's not what that is. This is a picture of X. And so in X, you see lots of spheres, and you would like to arrange that they intersect geometrically once. So here's, for example, here's one of the ascending spheres of one of those 2 handles. Here's another one. And the 3 handles, descending spheres, are basically the same as the 3 handles in this picture. And so it looks something along these lines. And you hope that you can cancel them, basically, is the name of the game. And you see nice, reasonably nice intersections. If you sort of zoom in on this picture, this green sphere intersects this red sphere in 3 points, but only once algebraically. There's sort of 3 points of intersection here, 1, 2, and 3. And you hope that you can sort of pair everything off nicely and cancel them. But it's pretty fiddly and pretty delicate. But the sort of main idea is that although these points, there are these 2 points here, there is sort of a nice looking Whitney disk because everything came to you as a ribbon. So there's it's almost a disk here. That's the point, is you can try to sort of do that Whitney move. You have a little bit of work to do to make sure you can really do it. Try to do that Whitney move to untangle these 2 spheres. If you're sort of careful and keep track of everything, you can cancel the handles. Anyway, so hopefully that answers your question. It's a bit of a ramble on there for a minute.
Thanks.
Other questions? Sorry, I have a very basic question. On your last slide, you said the unnothing number for the boundary of the disk should be exactly 2. Should it be 2 or less than or equal to 2?
Less than or equal to 2.
Yeah. Great, thanks.
Yeah, good. Good, glad you got that. Yep.
Other questions? So if there's, go for it.
What happens if you make the unnothing number 3? What breaks?
It's just not obvious that you can cancel the handles like this. Yeah, so we obviously we really wanted to get them all. We really wanted to try to show that doubles of all Gluck twists were standard, because that would have been great. But you get kind of stuck. Somehow what's happening is that you're using this 2 handle in a non-trivial way. And it's somehow you can only use it once in a way. And because you don't have more of them, you sort of get stuck. There isn't an obvious next thing to do. We tried a few things to make it sort of work, and nothing really worked. Yeah, I think somehow this this handle decomposition is interesting. I don't think it ever really showed up anywhere because a lot of standard recipes, or a lot of what you would try to do at the very beginning is always like cancel this handle. I cancel that +1 handle against like one of the 1 handles and then just like carry on and do Kirby calculus. And so from that point of view, this handle decomposition is not super useful because it's not obvious that it's not obvious how to cancel a handle there. But we had sort of other things in mind and we used it differently. But yeah, anyways, in short, you sort of just get stuck. It's not clear how to sort of keep canceling handles like this. So that answers your question.
Other questions? Great. So if there's no other questions, let's thank Patrick again. Thank you.
Patrick, it comes down for real sometime. Take it out.
Yeah, I sort of, it would be great to be back. I would love that. Yeah.
Thanks, that was a great talk. I'd like to stick around. I gotta run. So,
Yeah, no worries. But yeah.
Thank you very much. See you
What's that?
soon. I know, for instance.
Cool. Yeah, okay, well, yeah, no worries. It was great to see you, Dave, and everybody else. And Akram again, yeah, thank you very much for the invitation.
Thank
Real cool
you
to
for
be
the great talk. It was awesome. Thanks.
Cool. Yeah, I hope I sort of pitched it okay. I struggled a lot with like what to say, especially at the beginning, because I worried that like doing too much Kirby calculus would just be sort of meaningless unless you really, really wanted to follow it, you know. But
Nice.
cool.
Yeah,
Cool.
it was
Cool.
nice. Thank you.
Cool.
Perfect. Thanks. No, it was really
Cool.
great. Thank you so much.
Cool. Yeah, no,
Awesome.
thank you again. All right, well, enjoy the rest of the day and see you later.
Thanks. You too.
Cool. Bye.